Let's work another problem. A spaceship has left Earth's orbit and is on its way to the moon. So let's draw a diagram as we go about here. Here we've got Earth, we've got a spaceship, lovely. And it's accelerating at 20 meters per second squared for 2 minutes. So we'll put acceleration 20 meters per second squared in that direction. And it covers a distance of 1,000 kilometers. So eventually it ends up over here. And over here, we know that my final position is 1,000 kilometers. And I can say then my initial position was 0. What are the initial and final velocities of the spaceship? All right, so I'm trying to find V naught. We can say T naught is equal to 0. Over here, we know that it took 2 minutes to do this, so we know that my T final is 2 minutes, which, just to do a quick unit conversion, times 60 gives us 120 seconds. And then we also want to find V final. So we know the things we know, the things we don't know, and the things we're trying to find. And to be explicit about here, we have 2 unknowns, V naught and V final, that we're trying to find. So we need equations to find those. And specifically, we can't just write one equation that solves for both of those. We'll probably need 2 equations if we have 2 unknowns. So let's try V naught first. V naught, we need an equation that can have any of the things we know and V naught. And looking at our constant acceleration equations, because again, it accelerates at 20 meters per second squared for 2 minutes, so that's a single constant value, we can say that here, my final position is equal to my initial position plus V naught T plus 1/2 AT squared. We know most of the stuff on here, and what we don't know is we don't know V naught. So X naught we know. We now need to solve this for V naught. So some algebra to do that. We can subtract this term from both sides. I'll go ahead and rewrite this equation with that modification done, and I'm going to move the V naught T term to the left side because that's what I'm trying to solve for. So it kind of makes sense to me to put it on the left. And then whatever was on this side, I'm putting on the right. So I've just kind of swapped the sides here. This will be X minus 1/2 AT squared. We're almost there. We just need to divide by T on both sides. And we're left with V naught being X minus 1/2 AT squared divided by T. Now we could simplify this sum, I guess. If we wanted, we could say this is X over T minus 1/2 AT divided by T, so that T's cancel. It's kind of up to you how you want to do that. At this point, we have the information. We just need to plug in the information. So we'll say this is equal to 1,000 kilometers. I'm going to write that as 1,000 times 10 to the third meters divided by the time of 2 minutes or 120 seconds minus 1/2 acceleration was 20, time was 120, and we get a V naught of 7,133.33 meters per second. I'm probably more inclined to write that as 7.13 kilometers per second, using the 1,000 kilometers, sorry, 1,000 meters is 1 kilometer. So we have that. So far, so good. So that's our V naught. That's what we start at. Now we need our V final. So we look at our set of equations and we can say, well, I have this equation here. My V is equal to my V naught plus acceleration times time. I know these things now. I just found V naught. So I can plug this in. Again, trying to use just the base meters per second units to keep my life easy. Plugging in for acceleration and time. Evaluate that, and we get 9533.3 meters per second. Or again, I would probably be more inclined to write my final velocity is 9.53 kilometers per second. So we had a situation where we needed to find two different things, and we needed two equations to do that. And if we had started with this equation, we would have noticed that, hey, we still didn't know this one thing, so we would have had to do some more work there. We could have instead started with a different equation that only had the final velocity and didn't have the initial velocity in that case if we wanted to solve for the final velocity first.